Welcome to clickmyproject.com. We will discuss about the product for Aware, Asymmetric Write Architecture with redundant blocks, a high write speed STT-MRAM cache architecture. Next we discuss about the abstract for the product. Spin transfer torque magnetic RAM is capable of 4 cross high integrated density compared to the standard on-chip SRAMs. Because of its non-volatile nature, there is no leakage in STT-MRAM bit cells when there is not accessed. Therefore, the STT-MRAM has been investigated as a candidate for replacing the SRAM in the last level cache, and increasing the LLC capacity can reduce the cache miss rate and consequently improve the instruction per cycle. Due to the low utilization of LLC, the standby leakage of memory bit cells in the dominant of component of the STT-MRAM total energy consumption architecture. The spin transfer torque magnetic RAM is a promising memory technology for lower level cache because of its high density and non-volatile nature. However, the high write latency in the bottleneck to its widespread adaptation for the further on-chip memory processor. In this paper, we propose a new cache architecture, asymmetric write architecture within the redundant block, that can be improve the write latency and taking the advantage of the asymmetric write characteristics of 1T, 1MTJ STT-MRAM bit cells. Due to the nature of the storage of element of STT-MRAM, time required to the 1s to 0 position or 0 to 1 position is a non-identical. In other words, one of the state transition then other direction. In conventional cache, there the overall write latency is low, but the proposed Aware cache design is to improve the redundant blocks and add the redundant blocks and to improve the system performance level and to increase the latency level compared to the existing methodology, and to improve the write operation and to decrease the write processing time for the STT-MRAM cache architecture. Next we will see the flow diagram for the product. First of all, enabling time is mainly based on the tag and index offset pin allocation and the tag array allocation. The two type of process to be applied for the STT-MRAM architecture. Then the enabling processing time to be mainly based upon the tag array address and the tag directly address allocations. The index bit is considered by the 11 bits and 9 row decoding process and 2 column decoding process. Thus we row and column decoding process and to collect the address location and the tag for 15-bit address location. These the two address locations are equal to, and additionally tag allocation for 5 bits to create the writing operation for an redundant block in data array architecture. The redundant block is used to clean and dirty positions and write the data to the dirty position and to transfer the data to the clean position. Based on the two position, we applied the slow writing and fast writing for the different STT-MRAM processing, and to improve the high speed performance and to calculate the test results for synthesis and simulation process. Then the simulation process to processing the writing the data for the tag array, data array, and to compare the tag array position level, and the simulation results to passing the input data signal and to allocate the memory allocation and to read the output data result for the processing time. And finally we see the output for the product. The output for the product, just we run the Xilinx ISC project for the Aware design. This Aware architecture was developed in VHDL language and to follow the structural modeling technique for the Aware architecture design. then to select the simulation and to select the simulate behavior model. Process to be run the result and to compile is successful, then create the iSim project navigator. Then create the index location and to apply the index bit for the binary format. Then the row decoding process and column decoding process to apply the index position. The direct address allocations are to apply the or binary process. This the address is equal, then to apply the data transfer methodology. Then the slow write is to activate to change the additional bitting process for our the accept positions. Then calculate the simulation result and to synthesize the final output result for the aware architecture. Then the implementation result to be applied. Thus the RTL diagram to be described. The RTL diagram is to describe the processing level for our switching activities. Then the technology diagram is to display the what are the lookup table placements to be applied for the aware architecture. More or less the memory oriented process we calculate only for the switching activity for the RTL and technological schematic diagrammatic representation. Then go to the design summary. Then design summary we create the synthesis report, just the report to display the processing time and calculations. Then the time allocations to be followed by the 0.20 nanosecond for the aware design running time for our process. Then calculate the aware design delay time using the synthesis report results.